Hello, this is an introduction to the rotational motion lab. I'd like to explain this list of 7 different items, so we'll be prepared. First, this lab involves a heavy piece of equipment. That's the rotational apparatus. This piece is heavy and it's also secured on a metal stand with one very small clamp. So it is extremely important that you hold it securely or you ask somebody to help you when you set it up, just to make sure it's not going to fall on yourself, on somebody else. We do not want to break the equipment, and more importantly, we want to be able to perform the experiment well and get good results. So here the arrows point to the rotational apparatus and the clamp. So this clamp needs to be first clamped onto the metal stand, and then it needs to be, and then the rotational apparatus will be fastened on it. So when you fasten the rotational apparatus, it's on the short end, as shown in this picture. In addition, we're going to use a smartphone to measure the time using the app, and also we're going to use a hanging weight. It's important that you watch out for your cell phone just to make sure it does not get damaged in any way, and also always keep it secured. Do not leave it on the bench where any piece of weight can fall on it. There are 4 pieces of equipment that we refer to in the lab manual. First is the metal plate. The rotational apparatus is mainly a heavy piece of metal plate. It's especially made heavy because that provides a large rotational momentum for this rotational motion to make it stable. And besides that, we have a larger plastic driving drum and smaller plastic driving drum. All 3 pieces are glued together, so their rotational motions should be identical. We call the larger plastic driving drum because we actually wind the string around it so that when the string is pulled out, this gonna make the whole apparatus turn and have rotational motion. So is the smaller one. It's called driving drum because we can also wind the string around the smaller plastic drum. Drum means small plate. So that when we pull the string, that will equally rotate the entire apparatus. At the bottom, we have a hanging weight at the bottom of the string. We have a piece of weight hanging. The procedure. First, we wind the string either around the larger plastic plate or the smaller plastic plate. In fact, if time permits, we want to measure both for comparison. And then we're gonna just let it go. All right. What's really important is that when we let it go, some people might mistakenly think this is a free fall motion, but if you think of it, free fall motion is falling only under gravity, but in this case, there's a string pulling it, although it's falling. So this motion is not a free fall motion. We're going to talk about the exact pattern. So the pattern is not free fall, and a little bit later, we're going to reveal what it is. And what are we going to measure? This is a rotational motion experiment, and this is a classic experiment. It's an experiment designed to help us to reveal both linear motion and rotational motion. In addition, it also let us exercise applying our knowledge about the relation between linear motion and rotational motion. See, linear and rotational motion are 2 different patterns. And we're going to get some more details. So first, we're going to measure time using a smartphone's stopwatch. Okay, we do not call it a timer. We call it a stopwatch because timer is, in fact, an alarm. Second, we're going to measure the displacement, delta y, using you're going to choose one of these equipments, a meter stick, a student ruler, a caliper, or a measuring tape. And you want to explain why you choose the one based on the range and the accuracy for this experiment. Okay, and the last one, you measure radius. You measure radius of a plastic drum that you wind the string around. When you measure that radius, you're going to see which equipment is best designed for you to most accurately measure the radius, besides the range and the accuracy. So that's the measurement. We measure these three quantities. And this is a rotational motion experiment. And you noticed we're not really measuring rotation because a long time ago, we did not then have any sensor for directly measuring rotational motion. And a very well-designed experiment will cleverly translate the rotational motion into a linear motion, because linear motion is can be measured a lot easily, and especially for students. After the measurement, we're going to do calculations. And the first set of calculations involve this pattern. So first we need to calculate a few quantities, including the acceleration of a linear motion. So the exact pattern of this motion is a one-dimensional motion with constant acceleration. And I want to remind you again, this is not a free fall motion. So for this particular pattern, we have 5 quantities involved. If you count the quantities, there are 5 distinctive quantities in these 3 equations. So if you need to find out the unknown, you come to these equations, you need to solve a linear motion. So we do first solve the linear motion in this experiment. So this is, by the way, a review of chapter 2, the one-dimensional motion. This is one of the 2 special patterns. The first is a motion with constant velocity along a straight line, and this is a motion with this one is a one-dimensional motion along a straight line with constant acceleration. So that's a review of those 2 patterns, and also specifically, I want to make sure you have these equations ready. Then you say, hey, why are we having delta x here, but in the motion it's vertical? We call it delta y. You can just substitute x with y, and then all of these quantities will be along the y direction. The textbook happened to print the x direction. And I know usually for vertical directions, we are more used to use y. So then substitute, replace x with y. Well, this is a rotational motion experiment, right? So after all, we want to study rotational motion. So here I have a summary from the textbook about rotational motion, and this is a really nice review. And also this is a really nice reference and tool for us to solve the lab real-world problem. So in this chapter, we introduced the 2 new quantities. One is called angular speed or rotational speed. That is omega. Although it looks like a W, we don't call it a W, we call it a omega. Omega is the angular speed or angular velocity. And then alpha. Alpha looks like an A, but it's actually a Greek letter alpha that's used for rotational acceleration or angular acceleration. And of course, theta or delta theta means the rotational position or rotational displacement, and the unit is in radians. Omega is in radians per second, and alpha is in radians per second square. And keep in mind, these units help us identify the quantities. Okay, so those are, we call it 2 new quantities because we introduced the rotational displacement, the angle before. So it's really, we have a total of 3 quantities: rotational displacement, rotational velocity, and rotational acceleration. Okay, next in 7.2 section, we introduced a pattern. That's a rotational motion under constant angular acceleration. So this is a special pattern. And also, this one is parallel to the linear motion under constant linear acceleration. Similar to that pattern, this pattern also we have 5 quantities to describe this special pattern. In other words, this special type of motion, and 3 equations that relate different quantities. Okay, that's 7.2. 7.3, relations between angular and linear quantities. Okay, so in equation 7.10, the linear speed equals to radius of the rotational motion times the angular velocity. Okay, the radius is interesting because we have 3 pieces of equipment that are all rotating. We have the metal plate, larger plastic plate, smaller plastic plate, we also call them drums, smaller plastic driving drum, larger plastic driving drums. So which radius should this R be? Okay, the answer is it's wherever the linear motion is tied to the rotational motion. In the experiment apparatus, the string ties the rotation and the linear motion. Whichever plastic drum we wind the string around, the radius would be the radius of that drum. So keep that in mind so you know which R you're going to measure. We do not measure the radius of the metal plate. Keep that in mind. All right, so 7.123 are 3 sections that provide us the theoretical patterns and equations for us to solve this real-world lab problem. 7.11, alpha A equals to R times alpha. A represent linear acceleration. R represent the radius of the plastic driving drum that we wind the string around. And alpha is the angular acceleration of the 3 pieces in the rotational apparatus. All 3 pieces have the same rotational quantities because they all rotate together. They all start together, stop together, accelerate together. Okay, so you are going to be asked to do all kinds of calculations in this lab. And here you have all the patterns and all the equations summarized. If you still have questions, feel free to ask still. Okay, in summary, we talked about the safety for this experiment because we are using a quite heavy piece of rotational apparatus. So we want to make sure like people are safe, equipment is safe, and we perform good experiment. Number 2, the equipment and how to set it up. And then we talk about the procedure and measurements, calculations. Instead of giving you all the details of the calculations, you're provided the patterns and the equations. So make sure you ask any question just in case there's anything you're not 100% clear. And we have post-lab discussions. They can be answered again using the patterns and equations provided for those quantities. In the end, make sure you fill out the lab report and you give the lab report to your instructor to scan and make sure you stay on the right track. That doesn't mean every little detail is checked, which is not always possible. However, that makes sure you're not missing out a big piece. And make sure you give your feedback and suggestion, what you like about this lab that we like to keep doing and maybe doing more, what you dislike about it, and we want to consider any changes. And more importantly, we really rely on students to tell us what they're interested in and tell us what you can think of that we may do differently to make this lab better, because that's a very constructive feedback. And we really appreciate your feedback, and I hope you're enjoying this experiment. And don't forget, ask any question you have. Every question is a good question. The only bad one is the one you left in your head and not asking. Okay, enjoy.